video
Oh
things around.
God. And now everything is just a digital interface for a software implementation, like all the various, switchers and um like a an audio panel board, audio mixer.
Mixer, yeah.
Yeah, you can have a hardware audio mixer, but most days you're just getting a software one where all it is it's a USB device that, controls some software that actually controls the audio streams internally.
Okay, I think we're recording.
Okay. Um, I'd ask if you want to test it and, listen to the recording real quick, but it's
I
up
did.
to you. Oh, well then, good. I guess I'll share my screen. I totally didn't think about how I was killing time. I legit just wasn't thinking that through. Uh, oh, am I not going to be able to? Oh, no.
What?
I thought I wouldn't be able to for a second. Um, Surface reflection. Okay. Well, I guess we should get this party started. We're continuing on where we left off last 2 weeks ago, talking about surface reflection this time. I have not read ahead, and so I may be mildly scatterbrained trying to understand what the heck is being presented.
I mean, I have a lot of experience with this.
Well, that's good.
I've implemented the Fong BRDF, the Beckman BRDF, the GGX BRDF. Yeah, fun stuff.
So, surfaces scatter light, they reflect some of it back. So you gotta have two effects. The spectral distribution and its directional distribution. So the skin of a lemon mostly absorbs light in the blue wavelengths, but reflects most of the light in the red and green wavelengths. Therefore, when illuminated with white, it's yellow. It has much the same color no matter what direction is being observed from, although there are some highlights where it's brighter. But a brighter area is more white than yellow.
Yeah,
Whereas,
the BRDF stands for bidirectional reflectance distribution function. Bidirectional because no matter which point you look at from, like which view, it should give you the same result.
it gets to it down here. Well, it's just making a general distinction between the color changing and the not the color changing. The yeah, the spectral distribution, the color reflection and the reflection dependent on direction. You know. And then translucent surfaces are more complex. We have subsurface light scatter or transport, which, if light goes, it doesn't just bounce off the surface, it goes into it and comes out slightly farther away.
You have stuff like clear coat.
Oh yeah, then you have multiple layers or multiple materials layered on top of each other, which is probably a much later chapter.
Yeah.
Because it's all about combining it. So we have BRDF and BSS RDF, which will cover uh so BRDF is pretty much a subset of BSSDF where the SS is non-existent or non-contributing.
Well,
Okay.
you have the reflections distribution and the transmission distribution, and the BSDF combines the two into one.
Mm, Okay, so we want to we want to describe how much radiance is coming towards the viewer at omega naught sub-zero. Or is that out? Yeah, that's out. Omega out. And then, so that'd be the radiance at point P in direction omega O as a result of the incident radiance along the direction omega I. Um, okay, is this describing, I'm trying to just,
Incoming light.
oh, omega I is just the vector, and then L sub I is the incident radiance at omega sub I.
Yeah,
Yeah.
that bit
Okay.
before the commas. Yeah, just
Yeah.
saying it a different way.
I stands for incoming and O stands for outgoing.
Good to know. So this is nice demonstration of the situation we're talking about. Incoming and outgoing. How much incident light along the incoming is scattered from the surface in the direction outgoing. So this situation is describing a specific incoming light source and outgoing light direction. So it's at specific vectors. It's not the whole surface.
Well, depends, right?
Oh.
In path tracing, you have the light coming from the camera, and then it's coming from the light source. But the way you do it in path tracing, you bounce around until you hit the light source, and that's Li, the incoming radiance from that light source that you're trying to find.
Hmm. So here we have different changing L sub at the differential cone of directions, the differential irradiance at P, where we have d omega cosine of theta, and then our L sub incoming.
Yeah, I think they mean that it's dependent on something like roughness, the different cone of directions.
A differential amount of radiance will be reflected in the direction due to this irradiance.
State of the angle between, is it?
Okay, well, oh, the reflected differential radiance is proportional to the irradiance. That's confusing initially to me, but then I'm remembering that this book is declaring radiance. No, I'm thinking of something else. The differentiable radiance is proportional to the irradiance. God, now I'm getting radiance and irradiance confused in my head again.
I think that's just saying like the light leaving is proportional to the light coming in, right?
Yeah.
I think so.
Oh, well, maybe it's much simpler than I'm imagining it. Or I'm imagining it's more complicated than it really is. And confusing myself due to that. Yeah, the constant of proportionality defines the surface as BRDF, F of R, F sub R. For the particular pair of directions, omega incoming and omega outgoing. And so we have our BRDF, which at a given point is the point here, P in the middle of the normal here.
Yes.
Okay,
Yeah.
that makes sense. And then in the outgoing direction and the incoming direction, we
Then you
have,
have derivatives.
yeah, derivative of the, is that radiance? Outgoing radiance divided by the differential irradiance.
No, I think E stands for the energy, but I'm not sure.
No, that was the differential irradiance.
Ah, okay.
Yeah. I mean, that might, it all kind of does refer to an amount of energy. It's just whether it is over an area or a surface or a differential of that is also different. And then we substitute out our cone thing here. So we have the differential of the outgoing is divides by the incoming irradiance at omega I times cosine of theta I, the angle from the normal. It has to be that, right? Did it define that here, or did that define it in previous chapters? And then derivative omega
Yeah.
I.
I didn't see a definition for it.
I think it's between the normal and the either.
Oh, it's be incoming
Yeah,
because
it's
it's
between the
I.
normal and the incoming ray.
Yeah. Because this is just reflectance.
That's just the geometry term. Yeah, I can explain later, like the microfacet theory, and like how they handle these type of reflections.
Well, I think the book will go over it eventually. Can I get where is
Like, yeah, 4.1 was radiometry. That was the one with all the.
yeah, so so we got
Oh, okay, you were looking at that.
BSDFs is in chapter 9, and I'm trying to see if it goes into.
Oh yeah, there's the
Microfacets,
microfacet.
microfacets.
Yeah.
I mean, this is pretty much just a construction of the theory rather than the specific construction that we use to do simulation. And so it's kind of building up from nothing. And, it's sometimes super generic and not very specific, but the book does try to get through it rigorously.
Okay, fair enough.
Yeah.
I'm just looking back at 4.1, and it does look like the theta I is the direction between, or the angle between the normal and the incoming direction.
Yep.
I mean, that makes sense. Might be worth having this chapter open. Okay. Okay, we just discussed that.
By the way, reciprocity doesn't really matter if you're doing a normal unidirectional path tracer. It only starts to matter when you're doing stuff like bidirectional path tracing or forward path tracing or stuff like that, right? Because then you want the incoming and outgoing to give you the same energy.
I can see that.
And almost all BRDFs are not energy conserving. Like literally all of the most popular BRDFs have issues with like higher roughness being darker than it should be.
Do you mean energy conserving as in it loses energy when it shouldn't?
Energy conservation just states that the amount of incoming energy should be the same as the outgoing energy, right?
Integrated over the hemisphere. Yeah.
Well, one of the assumptions I've seen is that it's the same or less than. because maybe
Yeah.
the energy gets absorbed into the surface as
Yeah,
just
and actually Fresnel, especially Schlick's approximation, actually gives you more energy around the sides,
yeah,
right?
the Schlick approximation certainly kind of violates that because it is not a it's an approximation, not a perfect representation of it.
Yeah, but it's actually quite bad. Uh, you can get a better
Just
result depending on the vectors you use to do the dot product, right?
I was just gonna look it up for my own edification, my own memory. Yeah,
Right.
it's
You have cosine theta, right? There's two ways to do Fresnel, like two different vectors you can use. One is the half vector with either the normal or I forgot really. And the other one is the reflected vector with the outgoing direction. And the reflected vector with the outgoing direction actually is more energy conserving than if you use the half vector.
uh more energy conserving. That doesn't logic, but I'm pretty sure I'm over focusing on that.
Uh, Shit, maybe I can find an article that explains it.
I guess I'm just saying more energy conserving. The energy conservation is just an inherent property like communicability in math, or rather you have it or you don't. It's not a more or less, unless you're talking about it conserves more energy
Yeah,
and doesn't lose it to or it's more closer to a true energy conserving
yeah. Well,
formulation.
the normal Fresnel actually adds more energy, and with depending on which vectors you use for the cosine theta, you either add more energy or you lose more energy, and you kind of have to cherry pick. But
Uh,
that's because Fresnel Schlick's approximation is just an approximation, right?
when you say normal, you mean Schlick's approximation?
Yes.
Okay, just clarifying because Fresnel is I'm looking at this article, Wikipedia, and it's like, there's lots of equations here, and not all of them are obviously the equation for it.
Yeah, but like. Uh,
It's complicated.
the thing is, there exists a BRDF that's perfectly energy conserving, but it's so much noisier because it relies on so much more stochastic chances, right? Than a BRDF like GGX or Beckman or et cetera, which are not energy conserving, but they result in less noise usually.
Mm, I can see that being the situation. Um, but yeah. Uh, yeah, reciprocity to get back, try to get through this chapter. Incoming and outgoing are the same for all pairs of directions. Energy conservation, the total light reflected is less than or equal to the energy of incident light for incoming directions. Yeah, so this one is if you conserve, if you obey energy conservation, the light reflected is less than or equal to, it does not have to be equal to, it just
You
has
want
to be less than.
you usually test this with a furnace test, right?
Yeah. Yeah, I'm showing my understanding. I'm gonna look up furnace test just for
It's literally imagine you have a bowl in the middle and then you have a box around it that's emitting light, and depending on how much light is being reflected, right, you can see if it's energy conserving or not.
note to self. Googling furnace test does not give you the white furnace test. It gives you checking to see if your furnace is working properly.
Ah, yeah. I guess it makes sense.
I've done that
Um,
more times than I can count. Uh,
There was a paper by this animation studio that went into how to how to account for energy loss and or gain. No, just energy loss. Let me try to find it.
Can I? That's just shader toy. Okay. So yeah, the white furnace test is you have your material in a uniformly lit environment. So a furnace where all the walls are white, it should be the same color as the environment. Because there is no like the light coming from all directions is identical.
I found the paper. I'm gonna send it in the chat.
Awesome.
It's by ImageWorks.
Ah, okay. Did you find the same? Yeah, okay. Do you know which slide number? I'm just gonna search for furnace. Here we
Yeah,
go. Yeah.
yeah,
Oh, okay. I can see.
yeah. If you scroll up a bit, you can see like before and after.
Yeah,
Yeah, you can see it here.
that is a very bad white furnace. Whereas this one, the compression might eat it, but I can faintly see the outline of some circles here.
Yeah, but it's close, you know.
It's very close.
Yeah.
Okay, and then it doesn't probably have more. Actually, there's more. Is this another white furnace test, or is this just a gray background?
It's a white furnace test.
Oh. Let me zoom in a bit more. Okay, yeah, you can see that you can really compare the values here and here. The energy compensation compensates. Okay. Energy conservation is hard is my takeaway.
Yeah, but if I can find it, I will give you an approximation for energy conservation that works almost close as good as this one. I found it.
Awesome.
Yep, I sent it in the chat. It's a super simple approximation, but if you're using GGX, it actually kind of works. And we're using it at work.
Hmm.
Yeah, you should scroll down like a bit more.
Just trying to.
Yeah, that's it.
Hmm.
And you can see below how it does in the furnace test.
Yeah.
Alpha is your roughness.
Hmm. So your roughness squared times your normal dotted with the
VO
view.
direction.
Yeah.
Well, minus VO direction.
Ah, yeah, that annoying issue of your vectors pointing the opposite direction you think they are.
Yeah. But yeah, if you scroll up, you're gonna see how it looks without it.
is
like a bit below. Yeah, there.
oh. Yeah. Yeah, you could definitely see it's not correct.
Yeah.
Okay. That's awesome. Um, well, to continue on with the chapter, this is introducing two quantities. One is hemispherical directional reflectance. 2D function of total reflection in a given direction due to constant illumination over the hemisphere. But another way, total reflection over the hemisphere due to light from a given direction. Um,
Yeah, basically how much light reflects based on the direction.
so it's I think I'm getting hung up on due to light from a given direction. So it would still
Integrating.
Yeah, well, usually you think of light coming from the light source towards the eye, and that's why they say that.
mm-hmm.
But it's a bit confusing because in normal path tracing, you actually shoot rays from the camera. But it doesn't matter if the BRDF has reciprocity. I forgot
Reciprocity.
reciprocity. Yeah.
There's a song with that as the name, I think, and it's a racy song, but it's a good way to learn how to pronounce it.
Okay.
RESPECT. No, I
Oh,
think this is it's like integrating over the hemisphere kind of idea. That's what we're talking about here.
Yeah, but we usually don't integrate. We use Monte Carlo, and for that we also need the PDF, which is like what's the probability of choosing this sample, right?
Yeah.
And like the thing is, it's very easy to come up with a distribution function. It's a bit difficult to come up with a PDF for that distribution function, and it is extremely difficult to come up with a sampling function that correctly maps the distribution function, right? Because then you need to do multiple integrals. I don't know. I don't understand it completely.
yeah, that's like one of the hand wavy things is right now we're talking about these integrals and we don't integrate the integral. We just sample and we get closer to the integral.
Yeah, but that's why you want the PDF because with a BRDF, sometimes it gives extreme values and has a higher probability of choosing certain directions, but you want to integrate the entire area. So when you divide by the PDF, what you say is like you're normalizing the samples, essentially being like, okay, this has a very high probability, I'm gonna lower its contribution, or this has a lower probability, and when you divide by like 0.1, you're basically increasing the contribution from that sample.
Hmm.
And that's why importance sampling is really fucking important. Pun intended.
Okay, the hemispherical reflectance of a BRDF. Not P, rho HH. So we had rho HD up here, now we have rho HH. A fraction of incident light reflected by surface when the incident light is the same from all directions. So if the incident light is equivalent across the entire hemisphere, it's what fraction of it is reflected at a given direction.
Uh,
Can you say that again?
I mean, I'm just reading this. Hemispherical reflectance of the BRDF gives the fraction of incident light reflected by a surface when the incident light is the same for all directions. The same from all directions.
isn't that just diffuse?
That could be a very fancy way to say diffuse. I mean, we have the formulation has the absolute value of cosine of theta outgoing times the cosine of theta incoming.
Yeah, it's just the normal with the outgoing and the normal with the incoming, right?
Right. All divided by 1 over pi, probably because it's the hemisphere integrations.
Yeah, and then you have the BRDF, and yeah.
Guess I'm just trying to come up with a feeling for what this is representing, and
I'm wondering why it's 1 over pi and not 1 over 2 pi.
because it's a hemisphere, not a sphere, or
Wasn't
maybe
wasn't the area of a hemisphere big?
I think you're right. It is over 2 pi, but
Yeah,
it might be because it's there's you're multiplying the cosine terms. I'm not sure.
Well, I think you're just going along one side of the sphere, say from like bottom to top on the left, and that distance is pi.
Mm, sometimes I can get lost in the integration sauce. No,
yeah, I prefer sums. They're easier.
yeah. I mean, this next paragraph just goes on and does other things. So, BT, DF, transmittance function, it's the same as BRDF, but on the other side.
It's
And yet,
refraction.
uh,
Transmittance, it goes through the object.
oh, I am thinking of something else.
So like glass, water,
Right.
skin.
Oh, yes. Okay. Yeah. Okay. There's the light that hits a surface and comes back in the same hemisphere. There's the light that hits a surface and goes through it, which is the BTDF. And then
Yes.
when you slap both of them together, you get the BSDF.
Yes, exactly.
Yeah. Um,
Okay, now that I understand. This is basically the formula for path tracing minus the integral.
yeah. And now we have to add a absolute value because it might come out the other side where you're getting into weird negatives that shouldn't be there.
Yeah.
Ah, it's just a hack. It's not a hack, it's just a mathematical constraint.
Simplification.
That's a good way to put it.
Yeah. Okay, and now we have the famous rendering equation.
Pretty much. So we integrate over the sphere, and not hemisphere, of incident directions around P to compute the outgoing radiance in direction omega due to the incident illumination at P from all directions.
Yes.
I mean, gosh, it took 3 chapters to get here.
It just says that it's averaging the light from all direction at point P towards the camera.
Yep.
Die.
So scattering equation over the sphere or reflection equation over the upper hemisphere. Oh boy. So we did BRDF, now we have BSSDF, where we just go and make it even more complicated.
Oh, yeah, that's subsurface scattering, I think.
Yes, yes it is.
Yeah.
Bidirectional scattering surface reflectance distribution function. Okay, that's different than what you said, but it's effectively the same thing. I,
Yeah, I think they just like using fancy names for stuff you can explain much simpler.
yeah. I also kind of prefer subsurface because it's implicating how the material itself is diffusing it, but maybe that's just what I know. So we extend our function with by adding two or by splitting the point in twain into two. We have the outgoing point and the incoming point.
Mm.
And it just excitant differential radiance at point P0, P outgoing in direction omega outgoing. Incident differential flux at P incoming from direction omega incoming. So
I think the radiance that exits from points outgoing from the outgoing point, and then you have the light that's coming at the incoming point.
yeah.
Because they say exitant, which I assume just means that it's describes what light exits at that point.
Yeah, it's this book is you weren't here last 2 weeks or 3 weeks ago when we went excitant radiance. Where is it? Incident and excitant radiance. It makes a distinction between incident radiance and excitant radiance because of signs and easier to describe in the in the descriptive text.
Ah, okay.
Because it's sometimes not very clear what direction everything is going, and it's kind of nice to have that distinguished.
Okay, cool.
Like radiant excitance. I think this is. Wait, no. Yeah, okay, this is where it defines it. We have irradiance and radiant excitance, which is the same quantity but in a different direction.
The phi term is the radiant flux. That's looks like, yeah. Total amount of energy passing through a surface or region per space per unit.
Yeah. I think this term is useful, but also very confusing because we have irradiance with the ir in front of the radiance, and then radiant excitance, which has the same radian and like radiance, which is down here, but it's
I like to think,
radiant.
I like to think of the first I in irradiance is like incoming.
And then exit. Excitance. Okay, yeah.
Okay, yeah. That makes sense.
So BSSDF generalizes BSDF to account for light exiting at a different point. More difficult to evaluate than yeah, that's true. Yeah, it cannot be understated how many things in life have a non-trivial amount of BSSDF or subsurface scattering contributing to their appearance.
Yeah, you have skin, you have stuff like trees and grass and vegetation in general.
Those are the most obvious ones, but even things you wouldn't think of it are still have a portion of it to a non-obvious degree.
Persons.
Water droplets.
Oh, well,
Water in the air.
Wow.
Our
The
body.
clouds. The atmosphere.
yeah, the atmosphere
Mm,
has a
yeah,
ton of
true.
that. And that's just like volumetric rendering is in a nutshell, is the light just goes everywhere
Yeah,
and
that's
comes from
why.
everywhere.
Oh, that's why you use the multi-scattering approximation from the Oz movie. I'll find it.
So we need to, if we wanted to generalize it, we have to integrate over the surface area and incoming direction, which makes this equation bigger.
I just
Oh.
sent a link. I use this in my latest clouds that maybe I can showcase later.
Ooh. We'd be happy to.
It's literally just this formula on the bottom left.
Okay. Oh yeah, multiple scattering approximate. Yeah.
Yeah.
Oof. There
It's-
is. Oof.
It's funny how it's coming from the Wizard of Oz.
I know. This is peak paper writing, paper title.
Yes, exactly.
Okay. Oh, okay. This is the end of the chapter. It is more complex. Mm-hmm. Oh yeah, and as you increase the distance between the incoming point and outgoing point, the contribution decreases generally.
I wonder how you account for both scattering and absorption, right? Especially like with more complicated materials that have like maybe even dispersion inside of them. Is that possible?
I'm not the person to ask.
Oh well.
Well, I think that's a good place to stop. Next week we can go over light as a non-geometric concept. Sorry. Where was the I mean, radiometry has a ton of like all of these quantities, energy, flux, irradiance, but it's still not really getting into the wavelengths.
Okay.
Because one of the confusing aspects is we have all of these terms, but they're not what we experience as humans with our eyeballs. They're more just physical math, not physics.
Yeah, yeah.
And then to take them into our eyes domain, we have luminance, which is the apparent brightness rather than the intensity, which is the actual brightness. Like the amount, if you were to measure the number of watts versus, wow, that looks really bright kind of thing.
Yeah.
And so yeah, we have radiometric versus photometric. And oh my God, these are some of the most nit, lux, candela. You can use these terms, but they're no fun to work with compared to joules, watts, and the combinations therein.
Or nits and k-nits.
Oh God.
We use nits and k-nits at work actually. But yeah, can I share my screen or?
Yeah. I think we're done with the chapter, so I'll stop